Welcome to Presentation 27. Today we're going to talk about the temperature and humidity sensor, the DHT11, DHT11. So let's start by looking at the architecture. So the temperature humidity sensor belongs to our layer 3 architecture. Now we're going to be using from the layer 3 the display functionality, and from layer 2 we're going to use the SPI framework, IO port framework, timer counter framework, and external interrupt framework. So let's look at the agenda. So today, first I'm going to start with making a presentation on the sensor data sheet, followed by the description of the sensor, how it functions, and finally we'll go through a sample program and then the summary. So let's start with the sensor data sheet. This is the document that I use to get all the information on how to program the DHT11 temperature and humidity module. The first page, it shows us some product overview. Next, I would like to mention that I highlighted the areas which I consider which were relevant for this high-level view of the document. So we have the sampling period, which they say is going to be greater than 2 seconds. In our case, we're going to be using 3 seconds. Next, it has the pin descriptions. So we have the voltage, one data line, because we are going to communicate serially with this temperature and humidity sensor, and then it has the ground. Next, here it talks about the serial communication. It has a description. In the description, basically they're going to tell us how the serial data is going to be formatted. Basically it says we're going to have 8 bits of humidity, which is the integer portion, followed by 8 bits, which is going to be the decimal portion for the humidity. Next comes the temperature. The temperature, we're going to have 8 bits of temperature, the integer portion, and then we're going to have 8 bits, which is the decimal portion, followed by the parity. Also, in red here, they note that they are not going to be sending the decimal portions, so we don't have to worry about it. Next down here, we have the timing diagram. And basically what these 3 lines are saying is that we're going to have to send a start command, which has a very specific format. And once we send that start command, the unit will reply with the measurement of the humidity and temperature as I show in the format I just showed you. Next, it shows the signal description for the serial. And here I outlined 2 items. One, let me increase the size. Here they are saying that a bit 0 is going to be a signal that has between 26 and 28 microseconds of duration. So it goes low, then it goes high, and if it lasts between 26 and 28, that means that's going to be a 0. And it also states here that if the signal goes from low to high, and the high lasts for 70 microseconds, that's going to be considered a 1. Now, I would like to also mention that these 70 and 2628, they're approximate numbers. So we're going to, when we program, we're going to have to tweak that a little bit to make sure we understand what is the amount that they can increase or decrease, I would say, the tolerance of those signals. Now next comes application information, followed by something called temperature effects, and license agreement, and warning and personal injury. So that's the end of the and some quality assurance. So that's the end of the document. It's a short document, few pages. However, each page has a lot of information. So let's continue with the presentation where I can translate what's in this document to code. Okay, so let's continue. Let me go to the next. Okay, here we are. So this is what the module looks like. Let's look at the module interface. So it has a power. So that's this pin here where you put the power. Next, it has the data output. That's temperature and humidity data. So the serial, which is this pin here. And finally, we have the ground connected to the ground. So how it works. The DHT11 contains a resistive humidity sensor and a NTC thermistor to measure temperature. Now it has an 8-bit microcontroller that processes the readings and sends them out as a serial data. The sensor is factory calibrated, making it easy to interface with our microcontroller, basically. So let's see at the flow of the data. So we send the start signal. Then after we send the start signal, we're going to get a 40-bit message. Once the 40-bit message has arrived, we will extract the temperature and humidity from the message and then display that information. Next, we wait 3 seconds and we do that over again to get a temperature and humidity update. Now this shows you the code and how the start signals works. In our case, what we're going to do, we're going to set our pin, which is the capture pin, to output. Then we're going to set it to low, wait 15 milliseconds, set it to high, and then after 20 microseconds, we'll set it to input again, so we can get the input information. So let's see how this works. So when we start, we have a signal low. So when we have our signal low, the first thing we do, we set the interrupt to trigger on rising. As soon as the signal rises, we're going to have an interrupt, and we're going to capture the time, which I call it T1. Next, we're going to set the interrupt to trigger on falling edge. As soon as we get the falling edge, which is going to trigger the interrupt, we capture the time. And after capturing the time, we set the interrupt to trigger again on rising edge. Now the pulse duration is going to be T2 minus T1. And as I noted, the direction is going to tell us whether this is a 0 or a 1. So let's see how this works. So this is the interrupt. So we disable interrupts. So when we started, it's going to be, the edge is going to be rising. So what we do is we get the value of the clock. Then we change the edge to not rising, and then we set the capturing to falling. So we did this, we capture the time, now we set it to trigger on falling edge. The next time it comes in, we're going to again grab the time, and then we're going to ask if the starting time is greater than the final time. I'm sorry, the final time greater than the starting time. The reason I do this is because I want to find out whether or not the clock has rollover while we were doing this activity. If the end time is greater than the start time, then I can say that the message, the pulse duration is going to be T2, which is the end tick minus the start tick. Otherwise, I know that there was a rollover of the clock. So in that case, my value is going to be 65,536, which is the largest value of the clock register, minus the start tick plus the end tick. And that's the value, the pulse duration. Next, I'm going to set the edge to rising and set to trigger on rising edge. That's basically at this point. And I'm going to increase my inhibiting, my in bit, I should say. When my in bit is greater than 40, that means that I had gotten a complete message. So what I do in this case is I go and calculate the value that I got. I again enable my interrupt, and then I set this parameter, which is going to tell the main program that it's time to request a new temperature and humidity value, and then we enable the interrupts. So basically this is doing exactly what I showed you in this figure. Now let's look at the sensor output equal to 0. So that would be, if it's between 26 and 28 microseconds, which is 448 ticks by the way, the sensor output is going to be 0. If it is 10 microseconds, the sensor output, it's a 1. I have to evaluate it as a 1. So let's see how we do this. So the message 40, that's the message that was filled up by our interrupt routine priorly. So I have to take the first, I have to go from 0 to 40. So I take the first value divided by 16, because the message is in ticks and I want to convert them into microseconds. So I divide it by 6, and then I ask, is it greater than 68 or is it less than 72? If it's true, then I know that corresponds to a 1, and I have this called binary message, and I put the first value to 1 and increment the counter. Next, I take the next value, and let's assume the next value does not meet this line, these parameters. So then it falls to the else. Now, if the message is greater than 23, the message divided by 16 in microseconds is greater than 23 microseconds, but it's less than 26 microseconds, then I set it to 0. Now, once I fill up my binary message with 1s and 0, then this is how I'm going to have to read it. The bits 0 through 7, so it would be bits 1 through 8 in the word, is going to give me the humidity integer. The decimal, I don't have to worry about it. Then the values 17 through 24, which would be array 16 to 23, it's going to give my temperature. I don't have to worry about the decimal portion, and I can ignore the parity. So this is how I do that. So humidity. So I know the humidity goes between 7 and 0. So what I do is I want to convert this array into an integer. This array represents a binary. So what I do is I take the least significant and multiply it by 2 to the 0, which is 1. That's bit 7. Then I take bit 6 and multiply it by 2 to the 1. Then take bit 5, multiply it by 2 to the 2, which is 4. Then I take bit 4 and multiply it by 2 to the 3, which is 8. And I keep doing the same thing till I get to 128. And that's going to give me the humidity value. Next, I'm going to do the same thing for temperature. So humidity and temperature contains two integers, the humidity value and the temperature value. And then I'm going to call the LCD display to display the information. So let's look at sample program 1. So let's look at the wiring diagram, the schematic I should say. So the temperature humidity sensor is hooked up by one line to the PV0. That's the capture pin, input capture pin. And it's a serial data bus, just one line. Then I'm also going to hook up the display, which I have my MOSI clock chip select, where the data command and the reset. So let's see what the sample process. The microcontroller will retrieve temperature and humidity data from the DH11 sensor. Second, the microcontroller will request updates reading to the DH11 sensor every second. It will get the data, and by the way, it's going to request it every 3 seconds. The microcontroller will transmit the latest value to the display, and which is going to show humidity levels, percentage, temperature in Fahrenheit, and then temperature again in Celsius. So let's look at the code. I'll start by first giving you a global view of the program. So we have here a routine init capture, which is going to initialize the capture of the technical signal. Then we have the enable and disable interrupt routines, which are going to enable and disable the interrupts. Then we have here the new temp and humidity routine. What it does is going to request a new measurement, which is the start routine. Then we have a routine here which is going to calculate the temperature and humidity. Next, we have a routine to display the data. Now here we have the main routine where we initialize whatever needs to be initialized and so forth and so on. And here we have the interrupt service routine, which is the routine that actually does all the heavy loading. So let's get into the details. So the first one, the init capture. What I'm doing here, I already showed you how to do it in presentation 10. So I'm just going to glass through this. So the first thing I do is I figure out whether I need the prescaler or I don't. Number that I have to measure is between 70 microseconds and as small as 20 microseconds. And we can do that fine without a prescaler. The next thing I do is I set the capture to be on rising edge, because that's how we're going to start first. And then I enable the interrupts. So the a rising edge is going to trigger an interrupt. That's what this line is doing. Next we have the enable and disable interrupts. That's just calling out the SEI and CLI routine. Here we have the new temp and humidity request. So what I do here is first the data is going to be stored in something called message 40. So every time I request a new measurement of temperature and humidity, the first thing is I set the array where the data is going to be stored to 0. Next, I have to send the following signals to request a new measurement. So the first thing I do is I set my port B to output. Next, I set it to low, wait 15 milliseconds, set it to high, then wait 20 microseconds, and then I set the port B again for input. Next I have here calculate the temperature. So I'm going to get this array, which is the message 40, and what it contains are ticks for the duration of the signal. So now based on that, I need to figure out whether they had transmitted a 1 or a 0. Now I take the message. Now I have 40 messages, so I go from 0 to 40. So I take the message and divide it by 16 to convert the ticks into microseconds. So now if the value is greater than 68 but less than 72, that means the value that I got from the sensor is a 1. Or the value that I got from the sensor, I should say, represents a 1. So I place a 1 on the correct place of this array, and then I increment the counter. Now, if the value is not within these parameters, then I check to see whether or not it is a 0. If the message is greater than 23 but less than 26, then I can say that this value is 0. So I place a 0 in the binary message, and then I increment the counter. Now, after this operation, what I've done is I put the value that we got from the sensor into the binary message, and they are ones and zeros, not ticks anymore. So now I have to convert those values to a integer. So how I do that? So I know the humidity value is going to be in position 0 through 7 of the message. So the way I convert this to the message is as follows. I take the least significant and multiply it by 2 to the 0, which is 1. Then I add the next one and multiply it by 2 to the 1, which is 2. Then following 2 to the 3, which is 8. And then so on and so forth till I get to 128. And when I add that, I'm going to get the value of humidity. Now the temperature, it is between position 16 and 23. 23 being the less significant. So then I do the same operation, take the 23 times 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, so forth and so on. And so now humidity and temperature contain two integer numbers. And then I call the HT-LCD display routine to display the information. So let's see, here is the HT-LCD display. How do we do? So the first thing I do, this temperature, humidity, these are global variables, which I calculated in this routine. So then I create a new parameter called TF, which is the temperature in Fahrenheit. So I just apply the formula for Fahrenheit. And then I have a string value. So the first thing I do is I clear the display screen and set it to green. Then I'm going to display the H percentage column, and I want it to be in color blue, and the size is going to be a 3. Now in my last presentation I showed how to do size 1 and 2, and this one I used 3 because it looked better on the size of display that I had. And then what I do is I use this UTOA function. So let me explain what this is doing. This routine, it converts a number into text that you can print or display, or a string. Now, the parameter value is the number you want to convert to string. The buffer is where to store the result, or where the result is going to be stored actually. And base is the base system. So let's look. So H is the humidity. I have it here. Global value. So the value H is going to be converted to base 10, and it's going to be stored in a string in the SDR2. So once we do that, then we can write the 3 by 3. We're going to write it in blue, size 3. This is the SDR2 is what got converted to a string from integer by the UTOA routine, and then we have where to place it in the 90,80. Now we do the same thing for the temperature in Celsius and temperature in Fahrenheit. So that takes care of the LCD display. Next we have the main. So in the main, we're going to call something rising edge, because that's where we start. And then we're going to initialize our capture, our ports, SPI and TFT. We need to initialize that because those are programs that we included for our display. Next, we're going to fill up the screen in color green. Wait 1000 seconds. We're going to enable our interrupts, and then we're going to write in black hello world. Wait 200 milliseconds. So at this point, what we have is initialize whatever needs to be initialized, and we place in the display the word hello world. Next, we start by requesting a new measurement. As soon as we request a new message, we're going to get into our loop. Now the first thing we ask is get new message equal to 1? And the get new message to start is going to be 0, and then it's going to be set to 1 by the interrupt service routine. So basically we do nothing here till the service routine says, hey, the get new message is equal to 1, which means that the service routine already calculated the value of temperature, humidity, and it has been displayed. So once we get that is true, then we wait 3 seconds. We set the get new temp to 0, and then we request a new value. And then we keep going, doing nothing till the interrupt routine again sets this to 1, and we request a new message. So let's look at the interrupt routine. So first thing I do is I disable the interrupt. Next, I ask, hey, is this a rising edge? And to start, it should be a rising edge. So yes, it's a start rising edge. So the first thing I have to do is I need to record the time when this happened. Then set the edge to not rising, and then change the capture to falling edge, to falling edge. Now, the next time this routine gets triggered, the edge is going to be not rising, so it's going to go to the else. So what we do with the else, the first thing we do, we grab the clock value. And then we ask, is the end tick greater than the start tick? If that's true, that means we subtract and put the value into the message 40 that has, it's going to end up with the 40 values, the message. Now, if that's not true, that means that we've gone to the end of the clock and we're starting again. So what I need to do in that case is I need to subtract the 65,536 minus the start tick, and then I need to add the end tick, because at this point the clock roll over, so I need to account for that. So then I place the value into the message 40. I set the edge to rising again, set the trigger to be rising edge for the capturing, and then I increase my inhibits. Now, when my inhibits gets to 40, that means that I received the complete message. So what I do in this case, I'm going to set the inhibit to 0 first. Then I'm going to go and calculate the temperature, humidity. And when I do that, like I showed you, the sync is calculated and also displayed. Then I'm going to enable the interrupt, and I'm going to get new TMP to once. So the request, we get a new request for data, and then enable the interrupts. So let's look at the output. So here you can see the hello world, and then the temperature, the humidity, the temperature in Celsius, and the temperature in Fahrenheit. So let me show you the start again. So we have in black color hello world with the screen, and this shows you also how we set up the value of the size to 3 from 2. The size of the font. So here you have a font 3. So here you have a humidity percentage, temperature in 26. So having the letters larger, it looks much better for the fills up better in the display. So anyhow, that gets us to the end of the program. We showed you the output. So let's continue with the presentation. Okay, so let's next we get into the summary. So in today's presentation, I showed you the data sheet and showed some of the highlights of that document. I gave you a description of the sensor. I talked about the sensor functionality. And finally, we went through a sample program. So I hope you've enjoyed this presentation, and hopefully I'll see you in the next one. Again, thank you very much.